All right, we'll start today's class with a quick rundown of the exam results. If you're faint of heart, maybe want to hide your eyes for a second. Anyway, so it wasn't great, I'm not going to lie. But again, these are all averages, so that doesn't mean individual results. I'm not reflecting on anybody's individual results. So anyway, if you recall, the first midterm had an average of 13, which is pretty typical. This one we were down to 10.6 as our average. A little bit lower than last year, so I don't know the reasons why. Honestly, I don't. I'm trying to figure it out, so not being... and then, you know, that said, keep in mind this is only 20% of your grade. There's still 54% left on the third midterm and the final, so treat that as an opportunity to improve. If you live your life as one giant sports analogy like I do, you know, quitting now would be like giving up at halftime. So, you know, you got plenty of time. You just got to make some adjustments and go after it. So now, in terms of what I can see, obviously I don't know all of your, you know, study habits, and I'm not a stalker or anything, so I have no idea what you guys do outside of class. But I can see in Blackboard what the one thing I can track, which, as we said at the beginning of the semester, does correlate with how well you're doing in the class, is number of homework attempts, and there does seem to be a general downward trend. So this is where we were in the first week. A little bit of an outlier in week 2 because many of you did the wrong assignment that week. But then since then, we've been kind of trending downwards in terms of the number of homework attempts per student. This is per student, not total. So, you know, people are dropping here and there. But, you know, this is the total number. This is the average homework attempts per student, and it is going down. So even though the material is getting more difficult, a lot of us are not putting as much effort, which is understandable because every other class gets a lot busier this time of year too. But if you really want to keep it up, and if you want to at least partially explain why there's always a drop-off between midterm 1 and 2, that could be part of it. So that said, you know, the drop deadline, as you'll recall, is this week. So if you're thinking that you're on the bubble and not sure if you want to stay in the course, I'm happy to offer you advice. I won't tell you what to do, but I will give you sort of a clearer picture of where you stand and what the possibilities are. Because keep in mind, everybody is, you know, possible at least for you to improve your letter grades by at least 2 letter grades, if not more. So really, you know, like I said, it's still really early on, still a lot of chance for your grade to change from here on out. All right, so with that sort of uplifting beginning, of course, we're going to go into now the topic that, if I'm being honest again, is one that every semester is almost one of the least favorite, okay? So we're going to transition right into something that everybody hates, which is great. Now, what I want to say about that, though, is the topic we're going to cover for most of today, which is lattice energy and Born-Haber cycles, it really drives home the point of, I think, why there's usually a drop-off between exam 1 and exam 2, because this approach we're going to learn today has a lot of steps to it, and you might be like 90% sure on each of the steps, but if it's a 5-step problem, that only gives you like 50% chance of getting it right. And the same for a lot of the questions on exam 2, where you might have known the individual steps pretty well, 90% or more, but if you're doing a problem that has 4 or 5 steps in it, and you only know each step 90% of the way, you're going to have, and especially in a binary test like we have, either right or wrong, you have at least 50% chance of getting it wrong. So I think it really drives home the point, and hopefully we learn from that from the second exam, that we have to be very detail-oriented and really know each of the steps equally well. We can't gloss over anything. And that's really what's required to be able to learn what we're doing today. So what we're going to cover today is really, if you're following in the book, is back in Chapter 3. So you'll notice that when I had the title slide, one of the sections that we're covering today is Section 3-4, way back in Chapter 3, because for some ridiculous reason the textbook introduces this in Chapter 3 before we've covered anything about enthalpy, stoichiometry, chemical reactions, all that stuff. So it was, you know, a ridiculous time to cover that topic, and now it's at least a slightly less ridiculous time to cover it, so let's go into it. All right, so we're going to talk today about the energetics of ionic bonding. So, you know, thinking back to what we learned in Chapter 3, ionic bonding is a bond formed between oppositely charged ions, positive and negative, positive from the metal, negative from the non-metal. We're going to be talking exclusively in this section about binary ionic compounds, so compounds that just have 2 elements, a metal and a non-metal, no polyatomics to deal with here. And if we can think about this, we can break down the steps that are involved in forming an ionic compound. So if we take a metal and a non-metal and we form an ionic compound, what we can do is we can recall that the ionization of the metal is one step that's going to happen. So let's say we have potassium and we ionize it to K+. So let's say we're going to make KCl as our compound, which has K+ and Cl-. One step that would be involved in forming KCl from the elements would be to take potassium and ionize it. So this is the ionization energy for potassium. It's the first ionization energy, as you recall, because it's removing the first electron. And the number for this, which is not something you'd be able to know off the top of your head, is 419 kilojoules per mole of potassium. I'll leave the per mole out, but it's understood to be per mole of substance. Now the other step, where did the, oh jeez, is also spazzing out on the screen, not just on my screen, okay. All right. Why is that phase shifting now? Oh, Jesus. All right, let me try closing and reopening this. Could be the resolution getting messed up because I already had this open before I hooked this up. All right, let's try this again. Alright, well I guess this slide is permanently foobar, so let me erase and start again. Alright, so we had, now that I'll try to line it up better this time and hope that the... Alright, so we're considering the ionic compound KCl, let's reboot. And we said that one of the steps would be ionization of the metal. So we're going to ionize the metal to make the non-metal. Sorry, the metal cation, and then the non-metal is going to be also take the electron afterwards. So the ionization energy for this is 419 kilojoules, and then the other step, which would involve the formation of the negatively charged chloride ion, is to take chlorine gas and add the electron to it, chlorine atoms as in the gas phase. We talked about this also in chapter 2 and 3 as being called the electron affinity. So the electron affinity for chlorine is a negative number, minus 349. We talked about how for most elements the electron affinity is negative, meaning that there's a net attraction when you add an electron. So we have these two steps involved. So what we've learned now in the most recent section of the course is that if we have two chemical equations and two delta H's or delta E's, however we want to interpret these, for those equations we can add the two equations together and we can add up the change in energy as well. So for this process here, if we add these two up, we have gas phase potassium plus gas phase chlorine going to K plus and Cl minus in the gas phase as well. So basically the electron that we have is an intermediate that cancels out. And the delta H for this process, each of these terms, the ionization energy and the electron affinity, are enthalpy changes. So we can add the two together using Hess's law. So the delta H for this process is just the ionization energy of potassium plus the electron affinity of chlorine, and what we see here is that it ends up being positive. And something that you'll touch on in more detail in Chem 2 is that typically speaking, if you have a positive delta H, that means it's unfavorable. You have to put heat into the system to get this to happen, so it doesn't just happen spontaneously. It's a little bit more rigorous than that, but we'll use that argument for now. And the point is that if we're just talking about the formation of the ions, the formation of gas phase ions is not particularly favorable. Usually is a positive enthalpy change. This is one example, but you see many others with other combinations of elements where this involves a positive delta H, it's endothermic. So we have an endothermic process to form the ions, but this is not the only thing that's involved in forming an ionic compound. So if we think about the other steps that are involved, once we form the ions, the ionic bond is formed by attraction between the two ions that we formed. All right, so ion attraction, or what we call the ionic bond, is the electrostatic interaction of oppositely charged and as we've talked about in many different contexts in this course, when you form an attractive interaction between two oppositely charged ions, that is going to be releasing energy. That's going to be a delta H or a delta E that's less than 0. So this process of forming the ionic bond is going to have a negative enthalpy change. It's exothermic. So that's pretty much true anytime you have two oppositely charged things coming together, whether it's a proton and an electron or two oppositely charged ions as we have here. That's going to be a delta H of 0. In the gas phase, we can consider this process as being the two gas phase ions that we formed making just gas phase Kcl, so basically one ionic bond between potassium and chlorine and making this sort of gas phase Kcl molecule, where in this case we can estimate delta H to be around negative 500 kilojoules, so this one being a very negative enthalpy change as we expected. However, this is not the most useful one for us because ionic compounds don't typically exist in the gas phase. We're going to learn about this more in Chapter 9. So a lot of the topics in Chapter 7, 8, and 9 are kind of all linked together, so some of them won't make perfect sense until we get to all of them. But in this case, what we'll learn in Chapter 9 is that ionic compounds as solids, they typically exist as solids, and they have these sort of repeating arrays of positive and negatively charged ions. They don't just have molecules that are sort of distinct from each other. So what we really want to think about is the energy involved with this process. Taking the gas phase ions and making solid Kcl in this case, or whatever the ionic compound is, as a solid, because this is typically how ionic compounds exist in their normal state. And as we'll talk about more in Chapter 9, they don't really exist as individual Kcl molecules, but they're going to be these sort of repeating arrays of positive and negative ions that go on forever and ever and make these regular solids that are called ionic crystals. We'll learn all about that in Chapter 9. All right? So this is the sort of process that we want to consider today. What we're going to learn today is how to figure out the delta H for this process, which the importance of this is not going to be immediately obvious in this course, but with some things you'll talk about in Chem 2 and later on in chemistry, this is what we call the lattice energy or the lattice enthalpy, and this is very important for, it contributes to the solubility of ionic compounds, which you'll learn in more detail later on. It also contributes to their stability, some of their chemical reactions, depending on how far you go in chemistry, those things will become more and more important. But this delta H for this process here is called the lattice enthalpy or lattice energy sometimes. Those two are used interchangeably, so we'll abbreviate it as delta H lattice, lattice being the solid compound that forms is sort of synonymous with that. And this is always going to be an exothermic process. Okay, so again, it's taking oppositely charged ions and bringing them together. But the question is, how do we determine this value? This is not an easy value to measure experimentally because it's kind of difficult to access these gas phase ions in a controlled fashion and then have them sort of come together to make these regular ionic compounds. Is hard to do. So this is not an easy thing to do experimentally in the lab. We can't just go in the lab and, you know, willy-nilly generate positive and negatively charged ions in the gas phase, you know, come together, measure delta H and calorimeter and be done. It's not quite that simple in this case. So the way that this is done, what we're going to learn today is an application of Hess's law. So we talked about Hess's law recently as being the process by which you can take individual chemical equations, add them up, and then the sum of the delta H's will be the delta H of that combined chemical equation. We applied that in a lot of other systems, and we saw that one application of that was using enthalpies of formation to determine enthalpy changes for reactions. So all that stuff that we covered recently we're going to use today in what's called the Born-Haber Cycle. All right? So the Born-Haber Cycle, we're going to break down this lattice energy, this step of taking gas phase ions, combining them into a solid ionic compound. We're going to take that and we're going to break it down into a bunch of individual steps where we do know the enthalpy change, and then we're going to add them all together and get the overall enthalpy change for that step. So the Born-Haber Cycle is, we're going to learn all this series of steps, and as I said, it's several, so that's where this becomes a little bit difficult, is that there's just a lot to keep straight here. None of the individual ones are things that we haven't seen before. But it's a series of steps, and it starts and ends at the same spot. So the beginning and ending point of this cycle, it's called a cycle for a reason because it stops and ends at the same place. The beginning and ending points of this cycle is an ionic solid. So the solid ionic compound that we're talking about is both the beginning and the end of our cycle. I guess any arbitrary point could be the beginning or the end, but that's sort of how we think about this. And so as you go around this cycle, as you have a series of steps that start and end at the same place, the overall delta H as you go around has to be 0 because we're starting and stopping at exactly the same point. So there's no enthalpy change if, you know, remember, at delta H is final enthalpy minus initial enthalpy. The final enthalpy is whatever the enthalpy of the ionic solid is. That's where you're starting also, so final minus initial has to be 0, but the individual steps are going to all be non-zero. So as I said, this is an application of Hess's law. And we use it to find lattice energy or lattice enthalpy, that term that we just introduced. All right? And the way that we arrange this, so there's a couple of ways to sort of visualize this or to sort of organize the work that we do in these types of operations. So one would be to do it like we did other Hess's law problems and just write out the individual chemical equations and then make sure they basically add up to the lattice enthalpy, that process here. So basically arrange all the individual steps that we're considering and make sure that this is the sum of all of them. Now, as I said, it's often going to be a lot of steps, probably 6 or 7 on average. So doing Hess's law with 6 or 7 chemical equations can become kind of laborious and kind of tedious. So the way that I like to organize it is to actually set it up as a cycle where we start and end at the same place, and we go around this whole cycle and organize it that way. And so what we do then is we're going to put the steps that have positive delta H on one side. And there's no right or wrong way to organize this, but this helps keep everything straight, I think. And if we do everything in the same order also, the order that we arrange these steps is not, it has some flexibility as well, but we're going to try to do things the same way every time so that we can learn how to do this properly. So steps with positive delta H on one side, steps with negative delta H on the other. And as we go around the cycle and take all these individual steps, some that have positive delta H, others that have negative, when we add up all of those enthalpy changes, they have to equal 0. So we add up all the delta H's for the individual steps, and they have to set equal to 0. And then one of our delta H's, usually the lattice energy, but not always, is going to be unknown, and we're going to solve for that unknown after we set everything equal to 0 and just rearrange to get the one that is our unknown. So again, this will make more sense when we do it in practice, but we're going to treat this a little bit differently than the last Hess's law problems. You could do it the same way, but like I said, writing out 7 individual chemical equations and making sure they all add up correctly can be time-consuming, so I prefer to do it using what's called the Born-Haber Cycle and actually writing it as a cycle, as the name implies. So beyond what we've already introduced today, there's a few other enthalpy changes, a few other energy terms that we need to be able to do a Born-Haber cycle. All of these we're actually familiar with except for one, so it's nothing new. It's just how we're going to put them together at the end is the challenging part. So one thing that we need is the formation enthalpy. We introduced this recently also. Last week was a blur, so I can't remember if it was Monday or Wednesday, but we talked about formation enthalpy, and this is the enthalpy change when a compound is formed from its elements. All right, so this is going to be one of the steps in our Born-Haber cycle. So if we're talking about Kcl, the example that I started with some of those steps earlier, the formation enthalpy of Kcl, as a reminder, is taking the element potassium plus chlorine in the standard state. So chlorine in the standard state is going to be Cl2, remember. So it's going to be 1/2 Cl2 in the gas phase, which is its standard state, and forming Kcl. And this is our delta H of formation, which is, again, you don't have to know these numbers, but we're going to use these numbers to find the lattice energy at the end. So that's the delta H of formation for Kcl. One term that we need that we haven't covered yet, we'll talk a little bit about phase changes in Chapter 9, so this is technically a phase change, where we're not doing a chemical step, we're just changing from a solid to a gas. So if you have, we notice that the standard state for potassium is a solid, and that's going to be true for just about every metal element, is that its standard state is a solid. But all the other terms that we introduced earlier today that we're using, like ionization energy and stuff like that, those are all in the gas phase. So if our metal is initially in the solid phase during this step here, we need to also get it into the gas phase as a separate step. So we call that atomization or sublimation, which is the process of taking solid metal and going into the gas phase. So it's, as I said, just a phase change, no chemical change. So this enthalpy change is sometimes referred to as the enthalpy of sublimation. I'll often abbreviate it that way. And in most cases, it's going to be a positive enthalpy change, or I guess every case, because you have to put energy into a metal to get its atoms to escape into the gas phase. Like I said, we haven't talked a lot about gases yet or phase changes. All this stuff will kind of circle back once we've gotten through Chapter 8 and 9 and make more sense. But we're talking right now, again, about the process of going from the solid to the gas phase. You have to put energy, heat into that, so that's a positive delta H term, in this case 89 kilojoules. And then the last step that we often have to consider is the bond dissociation. So our nonmetal, in almost every case, is going to exist as a diatomic or sometimes higher order polyatomic molecule in its standard state. As I said, we're using the nonmetal in its standard state for this step. But the other steps involving the nonmetal, primarily the electron affinity that we talked about earlier, that's going to involve just the individual nonmetal atoms by themselves, not the molecules. So we have to consider the bond dissociation, which is again, breaking covalent bonds between nonmetal atoms. So once we organize this, it'll make more sense in a second, but we're going to have some steps involving the metal, some steps involving the nonmetal, and then some steps that involve the combination of the two to make the ionic compound. All of those are going to be sort of grouped together to make this Born-Haber cycle here. We just want to get the individual steps introduced and remind us what those are first. We haven't seen these in a while. So bond dissociation for chlorine would be taking diatomic Cl2 and breaking it up into gas phase atoms, just Cl by themselves. So this delta H we introduced earlier is called the bond energy or bond dissociation. And energy has a few different names, but it's that step of breaking a covalent bond, which we introduced back in Chapter 3. And that's going to be plus 244 kilojoules, okay, for this particular molecule, but it's different for every other nonmetal that we consider. So those are the steps we have. We introduced some earlier today, which was ionization and electron affinity. We have formation enthalpy, sublimation, bond dissociation. And now we have to figure out how to put all these together to start and end an ionic compound and solve for our unknown lattice energy. Okay, so here's what the Born-Haber cycle looks like. I gave myself a little bit of a template to handicap my terrible artistic abilities. And so this is kind of how I'm going to organize it. The number of steps could be slightly different from problem to problem. It's not always exactly the same series of steps as we'll see, but it's basically going to be, most of them are all going to be the same. So as I said, our starting and ending point at the bottom of the cycle, which is where I put it, is the solid ionic compound Kcl. And the step that we're trying to find delta H for is going to be the lattice energy, delta H lat as we call it. And that's going to be the process of taking the gas phase ions, K plus and Cl minus in the gas phase, and combining them to make Kcl. So we're trying to figure out what is the enthalpy change for this step, going from K plus Cl minus in the gas phase. Kcl is a solid. This is the delta H we're trying to find. And we're going to use all of the other steps that we've been talking about today to work around the cycle, get to here, and then once we go all the way around, the sum of those will be 0. So the first step is we're going to take our solid ionic compound and we're going to break it up into its elements. Because again, most of the steps involve the individual elements, but first we have to take our compound, which has the two elements together, and break it up into the individual ones. So the first step is going to be to take KCl and break it up into solid potassium, which is the standard state for potassium, and chlorine gas. We have to put a 1/2 there because we have to keep it balanced. There's only one chlorine atom in the formula, so there's going to be only 1/2 Cl2 that forms when we break this up. Now this step here, the process of going from the compound to the elements, is related to what? So if we go from elements to compound, what do we call that? That's called formation, right? This is the opposite of formation. We're going from the compound to the elements, so what is the delta H going to be then? It's going to be the negative of the delta H of formation, exactly. Okay, so this enthalpy change here is negative delta H of formation. Okay, because we're going in the opposite direction. The formation is going from the elements to the compound. In this first step, we're going from the compound to the elements. So it's going to be negative delta H of formation. And as we introduced earlier, the delta H of formation for KCl is negative 437. So the negative of that is positive 437. So this first step has an enthalpy change of 437 kilojoules. That gets us to the elements in their standard state. So once we do this first step, so when you do a Born-Haber cycle, first step is always the same. Break the compound up into its elements, take the negative of the delta H of formation. Okay? Then the second step is going to be, the next two steps really are going to involve the metal. So once we have the metal that's solid potassium here, we want to change it into gas phase K+. So there's two steps we're going to take to do that. The first step is going to be to take our solid potassium and change it into gas phase potassium. We just introduced that. It's called sublimation or atomization. So this step is going to be taking the solid K potassium and making it into gas phase. We're just doing one step at a time, so we're only going to act on one of the species at a time here. All right, so K solid to K gas, we saw that that was called sublimation enthalpy, sometimes abbreviated as this. And the number that we gave for that step was 89 kilojoules. Again, the numbers, all of them are going to be given to you except for one. You just have to recognize which one is which and which one you take the negative of and so on. So we'll talk some more about that in a bit. But that's the second step. Then once we have gas phase potassium, we have to change it into gas phase potassium ions. And remember, that step is referred to as ionization, going from neutral to positive by losing an electron. So we're going to lose an electron to make K+. So we still have the same 1/2 Cl2 gas, and then we have that electron that we liberated that's going to be sticking around. So that's going to be referred to as the ionization energy, the first ionization energy of potassium, and the number for that is 419. All right, so that number we gave you earlier, so that's one of the numbers. All right, so now we have gas phase potassium cations, which is what we want for our last step, so we're not going to do anything else to the metal, but our non-metal is currently as 1/2 Cl2. We want it to be Cl minus, so there's going to now be 2 steps involving the non-metal to go from 1/2 Cl2 to Cl minus. So the first step is going to be the dissociation. So we're going to take Cl2 and we're going to dissociate it into chlorine atoms. So we still have K+, then we're going to have 1 chlorine atom because it's 1/2 Cl2. Now we have to remember that the dissociation enthalpy for Cl2 is defined for 1 mole of Cl2, but here we only have 1/2 of a mole, so we have to make sure we multiply that by 1/2. Remember, if we scale the coefficients, we also scale delta H. So our delta H of dissociation, which refers to 1 mole of Cl2, now has to be written as 1/2 times that. So 1/2 times the number that I gave you earlier is 122. All right, and then the last step before we get to our ending point is we have chlorine atoms in the gas phase. We're going to combine them with this electron to make Cl minus. And remember, when an atom gains an electron, that's referred to as electron affinity. So this last step here of taking Cl plus electron to make Cl minus, that's called electron affinity, the first electron affinity of chlorine for being precise, and that has a negative delta H of minus 349. Okay? So now we have all of these steps where we have a bunch of numbers written here, we have one unknown, and as we go around this whole cycle, the sum of all of those will have to be equal to 0. All right, so that's what the Born-Haber cycle looks like. And then what we're going to do is up here, I didn't give a separate slide for this. Remember, the sum of all of these is 0. So 0 is going to be equal to this term here, 437, plus the 89, plus 419, plus 122, plus negative 349. So we're just adding these up as we go around the cycle. I'm leaving units out because I'm being sloppy, but you'll hopefully forgive me for that. And then the last step here is the lattice energy, which is our unknown. All right, so we now have a linear equation with one unknown. We solve for the lattice energy. Negative 718 kilojoules. All right, so that's our only unknown step, and that's what we get. When you're doing lattice energy problems like this, where you're calculating lattice energy, if you don't get a negative number, you did something wrong. I'll say that right now. Okay, so this is again another one of those things where, yeah, there's a lot of steps, but at the very minimum, you should get a negative number. If you don't get a negative number, then you know something was set up incorrectly. All right, so that's an example of a Born-Haber cycle. All right, let's try one here on our own. This one's going to be a little bit different. So this is how they're going to be set up now, typically on homework problems, which you'll get some practice this week. And on the test, there'll be one of these. We're not going to give you a ton of these problems. They take a while, but we'll give you one on the test. I can promise you that. So what we're doing is we're using the Born-Haber cycle to determine the lattice energy of magnesium bromide, which is MgBr2. And here's all the information. We have the sublimation energy of the metal. We have the ionization energy going from the metal to the metal 2+. This is a 2+ cation, so we need that whole step there. We have Br2 vaporization, dissociation of Br2, electron affinity of bromine, formation of MgBr2. All right, so again, the one way we can do this is to set up a cycle. So we're going to, this time I'm going to draw it out, so this is risky, but I should be able to do this. All right, so our starting point is the solid ionic compound MgBr2. And what we're trying to find again is lattice energy, which is going to be the two ions that make it up. So we have, in this case, Mg2+ and two Br minuses. So we have to separate the ionic compound into its ions, and those are the two that are combining, and that's the step that we're trying to solve for here, which is the lattice energy. Okay, so this is the step we're trying to get. So what we're going to do is we're going to do a series of steps that are going to take this ionic compound, break it up into the elements, and then ionize the elements to make the two ions, and then recombine them. All right, so the first step, as I said, is always going to be breaking this up into the elements. So we're going to have magnesium bromide decomposing into the elements in their standard conditions, their standard states. That's going to be magnesium solid. And we have to remember for this one that bromine, the standard state of bromine is Br2, and that it's a liquid. This is one of our only two liquid elements. Once we have this set up here, this again is our minus delta H of formation. It's the opposite of the formation enthalpy. We go up to the given information. Formation enthalpy is negative 524, so that means this term is a positive 524 when we break up into the elements. The next two steps are going to involve the metal. So we're going to take the solid metal and we're going to change it to gas phase metal. That's going to be the first thing we do. So for the metal, there's basically no variation. It's always going to be the same two steps. Sublimation followed by ionization for the metal. So our first step is sublimation to make gas phase magnesium atoms plus, we're not doing anything to the bromine yet, so it stays at Br2. So this is solid to gas. As we said, that's referred to as sublimation enthalpy. And when we go to the given information, they're not always going to be labeled the same, but we see that we have right here sublimation of magnesium, or it could be written as magnesium solid and magnesium gas, but it's that step here that we have to recognize, which is plus 148. Okay, so we're going to use that number here, plus 148. Next step for the metal, again, always the same for all these problems, is to take the metal and to ionize it into the cations. Here it's a 2 plus cation, so we technically have two ionizations to consider. We're losing 2 electrons from our metal, so we're going to make magnesium 2 plus in the gas phase, plus Br2, we didn't do anything to that. And then we're going to have 2 electrons. So this is going to be the sum of the first two ionization energies, ionization energy 1 plus ionization energy 2. Typically in these problems, we'll give them to you combined already. So if you go back to the given information, we have ionization of magnesium all the way to magnesium 2 plus. That's technically 2 ionization energies already combined for us. We don't have to do anything to that number. We just put it in directly, 2187. It's a much larger number because it's removing 2 electrons. So I'm not drawing this to scale by any stretch, but this is going to be 2187 kilojoules for that step to remove 2 electrons. So our metal is all set. We're at magnesium 2 plus. That's where we want to end up for the last step, which is our lattice energy step. The next thing is going to be doing the non-metal steps. So this one has one additional step because our standard state for bromine is a liquid, but the dissociation energies are for gas phase bromine, electron affinities for gas phase bromine. So we need to also, like we did for the metal, take our liquid bromine and change it to gas phase. Okay, so we're going to take this into the gas phase first. So that's going to be Mg2 plus Br2 gas, so just a phase change now, still 2 electrons, we haven't done anything with those. So this is what's called vaporization. Again, that'll be a process we'll learn more about in Chapter 9, but for going from liquid to gas is called vaporization. And for bromine, that's 31, that's the number on the previous slide. And then the last step here is to go we're going to dissociate the Br2 into bromine atoms. So we're going to take Mgb2 plus. These Br2 we're going to dissociate into bromine atoms. And then we still have our 2 electrons. This is our last endothermic step. This is our enthalpy of dissociation, which for Br2 is plus 193. And this time we don't have to modify this term. We're going to put it in exactly as written, because we have 1 Br2 here. This is 1 mole of Br2 when we balance this out, so we don't need to modify the step because dissociation refers to 1 mole of the diatomic molecule. All right, and then the last step is to take our 2 bromine atoms and our 2 electrons and combine them to make 2 Br minus. So again, it's 2 Brs, 2 electrons, 2 Br minuses are combining. This is the electron affinity step, but we notice that we now have a coefficient of 2 in front of bromine. So this is going to be 2 times the electron affinity. All right, because it's 2 moles of bromine plus 2 moles of electrons going to 2 moles of Br minus. Electron affinity, we refer to 1 mole of that process. All right, so it's going to be 2 times the electron affinity, which on the previous slide is minus 331. So this whole step will be minus 662. All right, so then what we have is, as we go around the cycle, we're starting at any here. So the whole thing added together is 0. Our first step is 524 plus 148 plus 2187 plus 31. So once we get the numbers written out, we just add them all together. We have negative 662 there. And then we have plus the lattice energy. Lattice energy is always a negative number, so even though it's a negative delta H, we just put it in as a positive. The only thing we put a negative sign in front of, as you'll notice, is delta H formation. That gets a minus sign. Everything else we don't put a minus sign in front of in this type of cycle. So the lattice energy when we solve for it is minus 2421 kilojoules. All right. So again, that's our unknown. We just move everything over and solve for it. So that's, again, the one way to set it up. Now, I know a lot of people don't like setting up cycles like that, and it takes a while. So there is a fairly generic equation that you can use to do this. I'm going to introduce it now. You don't want to become too attached to this because you have to think about the steps a little bit. You can't just blindly apply this equation, but it can at least help orient you and see if you're on the right track, and it works for, as I said, most of these problems with a few variations here and there. So if we have, I don't think I have a separate slide for this, do I? No. So if we have a generic ionic compound, so I'm going to put it on this slide because I have a little bit of room here. All right, so if we have a generic ionic compound that has some formula M with a subscript M, X with a subscript of little x, that basically means this is the formula compound. In the types of compounds we work with for lattice energy, M and X are going to either be 1 or 2. There's not really many possibilities, but for example, for MgBr2, there's 1 metal and 2 nonmetals in the formula. So these are just the coefficients in the formula, the subscripts in the formula. If we have this type of ionic compound and we want to solve for lattice energy, so we move everything over. So we take this equation here, which is set equal to 0, and we move everything over to the other side to solve for lattice energy in a more generic sense. The lattice energy is going to be the delta H of formation, and this is going to be for the ionic compound itself. Okay, so that's the first thing we put in. Then we're going to subtract 2 terms associated with the metal, and we're going to modify them by whatever this subscript is, because if we have more than 1 mole of metal in the formula, we need to modify the 2 steps for the metal by that amount. Because remember, if we change the coefficients of a step, we have to change delta H by the same factor. So we were going to do M times the sublimation energy for the metal. And another step for the metal is going to be M times ionization energy. And these 2 terms are associated with the metal. And again, if there's only 1 metal in the formula, we don't have to modify these by anything. If it's M2, like if we had M2, like a metal sulfide, like sodium sulfide, Na2S, you have to put 2's there and there. All right, then we have 2 steps associated with the nonmetal, which is going to be we have to do the dissociation. And so our nonmetal, we have X in the formula. That's the subscript on the nonmetal. So it's going to be X over 2 times the dissociation energy for X2. The reason it's X over 2 is because if there's 1 X in the formula, we only need 1/2 of X2 to dissociate. So that's just making sure it stays balanced. And then we subtract X times the electron affinity of the nonmetal X itself. Okay. So again, there's some variations on this depending on, in this step we had to add the vaporization energy for bromine. In other cases, if it's not X2. So this works if X2 gas is the standard state for the nonmetal. If the nonmetal has a different standard state, if it's sulfur, which is S8, there's some variations on this. And you'll see those in the homework, so definitely practice them, go over them with me if you're having trouble wrapping your head around the differences. But for most ionic compounds, the nonmetal is X2 gas. So if it's a metal chloride, it's going to be Cl2 gas as the standard state of the nonmetal. If it's a metal oxide, O2 gas is the standard state of the nonmetal. So for a lot of the compounds, this is going to be the format, and you can use this equation to find lattice energy and it'll work. But you do need to be aware of the variations that sometimes present themselves. And so the more you practice these, the more variations you'll see, and you'll get used to that. All right, so any questions on this process? All right, so the other thing we expect you to do with lattice energy is, so that's how we calculate them. And, there's not infinite variations on that because, as I said, we're dealing with relatively simple ionic compounds for that. We're dealing with, binary ionic compounds that are typically going to have either 1 metal and 1 nonmetal, or 1 metal with 2 nonmetals in the formula, or 2 metals with 1 nonmetal. Not a lot of combinations. So if you do a bunch of those this week on the homework, and this is where doing all 4 attempts of the homework can be especially helpful to see all those different variations, hopefully, there's really only a finite number of ways you can handle that, so you just have to get used to it. The other thing we expect you to do, which I think is a little bit simpler, is, and certainly less work, is to just predict or rank or compare lattice energy. So we give you 2 compounds and we say, which one would you expect has a larger or smaller lattice energy, okay? So if we have a lattice enthalpy, and we want to write it out as sort of an equation, we're not going to use this equation to calculate lattice energy, but if we want to get sort of an idea of what it's related to, it's going to be some constant, which is going to be ill-defined, and not really, we're not even going to try to define it here, but the factors that really matter are, it's the product of the two charges. So Q is the charges of the ions. So again, we're talking about ionic compounds here made up of positive and negative ions. So Q1 and Q2 are those two charges. And what also matters is R, which is the distance between them. So Q1 and Q2 are the charges of the ions in the formula. R is the distance that separates them. All right? So if we change the size of our ions, if we go from smaller to bigger ions, so if we go from, let's say, magnesium oxide and we move down the periodic table to barium sulfide, which has larger cations and anions, so we make the ions bigger overall, larger ions are going to result in a smaller lattice energy, because the farther apart that we put them, so if they're larger, they're going to have to be farther apart from each other. The farther apart they are, the weaker the attraction between the ions, and that contributes to a smaller, or what we say is less negative lattice energy. All right. When we say the size of lattice energy being bigger or smaller, we're referring to the magnitude. Lattice energy is always a negative number. So if we say it has a smaller lattice energy, that means it's less negative or less, or smaller magnitude. If we say it's a greater lattice energy, that means it's more negative or higher magnitude. So if we change the size of the ions from bigger to smaller, we're going to decrease lattice energies because there's this inverse dependence on R. And then if we look at charges, the higher the charges that we have, we get a larger or more negative lattice energy. All right, so more negative, again, being what we use is saying larger. All right, and we can see the examples above where this is clearly revealed. So we did two examples in class today of calculating lattice energy. And if you look at the final numbers that we got for MgBr2 and KCl, the biggest difference between these are the charges. So this one, KCl, is made up of +1, -1 cation and anion. This one is +2 and -1, so it has higher charge on the metal. And we saw that the lattice energy for MgBr2 was much larger, or a much more negative number, so larger in magnitude, as we said. So you can compare those two numbers that we just calculated and see that when we increase the charge of the cation from +1 to +2, the lattice energy increases by a lot. So those are the kinds of comparisons we're going to ask you to do, is some combination of charges of the ions and the distance between them. So an example of this type of problem would be, we'll give you a list of ionic compounds, and we say, which one of the following has the largest or most negative lattice energy? So we give you a list of compounds, and you pick out the one that's biggest or smallest, whatever the question asks. Now, as I said, there's two factors that influence it. There's charge and radius. The first thing you want to look at is the charge, okay? So charge first, then size. And the reason is that typically the compounds we're going to ask you to compare in this are going to be binary compounds with only two elements in the formula, one nonmetal, one metal. And so that means they're either +1 -1 or +2 -2. And so if we go back to this equation here, product of the charges Q1 and Q2, if you go from a compound that has a +1 cation and a -1 anion, and then you're comparing that to a compound that's +2 and -2, this product here is going to be 4 times larger because it's the product of the two charges, Q1 and Q2. So you're going to increase lattice energy by a factor of 4 just by changing the charge from +1 -1 to +2 -2. You're never going to change the radius by a factor of 4. All the ionic radii on the periodic table are within probably a factor of 2 of each other at the biggest. So the point is that the charge is the much more important factor, because just varying the charge by from +1 +2 to +1 -1 to +2 -2, that changes lattice energy by a much bigger effect than you'll ever see by changing the size. So we look at charges first. So if we look at the compounds, we go to the periodic table and figure out the charges of the cations and anions. So sodium fluoride is the first one. All right, and as we should probably know by now off the top of our head, sodium is in group 1, so it makes a +1 cation. Fluorine is in group 7, so it makes a -1 anion. So this first compound here has +1 -1 combination. Lithium fluoride, same anion. Lithium is also in group 1, so it's going to be another one that has +1 and -1 for the charges of the cations and anions. The rest of these, though, if we have magnesium, oxygen, magnesium sulfur, beryllium, oxygen, magnesium and beryllium are both in group 2, so the last choices are going to have +2 cations. Oxygen and sulfur are in group 6. Those are going to make -2 anions. So our last 3 answer choices here are going to form +2 and -2 combinations. Okay, that's the charge of the cation and the anion in these 3. All right, so now we have 2 that we can eliminate. As I said, look at the charge first. If we're looking for largest lattice energy, we want to find the one that has the highest charge. That's going to be the one that we pick. So these 2 we can eliminate. We would always expect a +2 -2 to have a higher lattice energy than a +1 -1, regardless of the sizes of the ions involved. Now we have to compare these 3 on the basis of ionic radius. So again, the bigger the ionic radius, the farther apart they are, and the smaller the lattice energy. There's an inverse relationship in this case. So if we compare magnesium oxide to magnesium sulfide in terms of lattice energy, they have the same cation, but if we go to the anions, oxygen versus sulfur, oxygen is here, sulfur is here. So which one's bigger, oxygen or sulfur? Sulfur is bigger, so we would expect the ionic radii for this to be larger, to be spread further apart. If the ionic radii is larger, that means the lattice energy is smaller. So in terms of lattice energy, which is the comparison we're making here, magnesium sulfide is smaller than magnesium oxide because O2- is smaller than S2-. All right, again, there's an inverse relationship between ion size and lattice energy. So if this has larger ions, it's going to be a smaller lattice energy. So we get rid of this one because we're looking for the largest of these, so that can't be the largest. And then if we compare MgO to beryllium oxide, magnesium to beryllium oxide, again, one of the ions is the same, oxygen, oxide, but we have magnesium versus beryllium. Which one is bigger? All right, magnesium is bigger than beryllium because it's further down in the periodic table. If magnesium is larger, that means the lattice energy is smaller, and that means beryllium oxide is our winner. Okay, because in this comparison, beryllium 2+ is smaller than magnesium 2+. So that makes the lattice energy of this one larger by that inverse relationship. Okay. All right, so the one that's going to be the overall winner then is choice E. It has the highest charge and the smallest ion combination, so that's the largest lattice energy. All right, so that's the other type of problem we'll expect you to do, is just comparing lattice energies, not necessarily computing them numerically, but looking at them and ranking them and comparing them to one another. And it doesn't really get any more difficult than this. This is all we're really asking that. So not a lot that we expect to do with lattice energy, but the calculations that we did as we introduced at the beginning of this class, they can be quite involved, so we're going to spend some time learning how to do those and practicing them. Any questions on lattice enthalpy before we move on? All right, so we are on to Chapter 8 now. And in Chapter 8 and 9, we're going to start talking about the states of matter. So Chapter 8 is gases, Chapter 9 is solids and liquids. And first thing we want to do is just give a real basic sort of definition of them, the differences. This is probably a review from many earlier science courses that you guys took. But if we have solid, liquid, and gas, these are all showing water molecules in those different phases. But any substance that can potentially exist in these 3 states of matter. So solid is a fixed volume and shape. All right, so it has a set volume, a set shape to it. And in terms of the molecular motion, which will be important for some things we'll talk about later in this chapter, solids, the molecules that make up solids, or the atoms that make them up if they're ionic compounds, they're not moving around a lot. They're pretty stationary. I mean, there's a little bit of vibration. Anytime you're not at 0 Kelvin, which is any time in your whole life. If you're not at 0 Kelvin, there's going to be some molecular motion even in the solid phase, but it's relatively small. They're just sort of shaking a little bit, not moving a lot. If we have a liquid, so a liquid has a fixed volume, so the volume is not variable, but it conforms to the shape of the container. Conforms, I think, not conforms, sorry. So liquids can change their shape to conform to the container. Another way of saying the same thing is that they have an upper surface, but they don't really have a defined shape anymore. So they're not going to spread out everywhere. They're going to have some surface that they're bound by, but they change the shape. You guys all know this, right? If you take a tall glass of water and pour it into a tray, the water is going to spread out to fill the tray. It's not going to stay in the shape of the glass that it came from. That's pretty obvious. So in terms of molecular motion, liquids have some amount of, they have a decent amount of motion in the molecules, but they're all kind of like rolling over each other. So they're still largely in contact with each other. It's still a condensed phase where the molecules are pretty close together, but they're moving about much more freely than they do in a solid, and that's what allows the liquid to sort of flow. As I said, solids and liquids are going to be the topic for Chapter 9, so we're not going to go into more details on those right now. But what we are going to talk about in this chapter is gases, and then we're going to do a pretty extensive study of those and different aspects of them. So gases completely fill the container that they're in. Did I spell completely right? I think I did. They completely fill the container. They're freely flowing. And in terms of density, they're the lowest. They have very low density because the molecules are spread very far apart. So in this case, the difference between liquid and gas is that in gases, the molecules are also moving around, but they're spread apart really further, and the molecules essentially have no attraction to each other, so they're going to spread out as far as they can. All right, so if I took a little, tiny container of gas here at the front of the room, let's say it was like the one that they use, so I think it's dimethyl sulfide that they use in natural gas. So you guys know natural gas has that smell, right, that warns you if it's present. That's not the natural gas itself. That's a little bit of an additive that we put in that has a very strong smell. So if I release some of that at the front of the room, a tiny little bit up here, over some time scale, people in the back of the room are going to smell it, and that's because those gas molecules will spread out to fill the whole room. They're not going to just stay put. They don't have real strong attractions to each other, so they just meander about and spread to fill whatever container they're in. And so that's the difference between those three states of matter, and we'll come back to solids and liquids later. All right, so one of the key properties of gases, which we saw a little bit when we talked about expansion work, is pressure. All right, so we introduced pressure when we talked about the expansion and compression of gases in the last chapter, and pressure is force divided by area. All right, so because we have gas molecules constantly in motion, they're going to exert a force on the container that they're in, and they're going to press against the container and exert a pressure. All right. So we're going to talk first a little bit about how we measure pressure on this slide. There's going to be a couple homework questions here and there on this. So one thing we can use to measure the pressure of the atmosphere that surrounds us is called a barometer. You're probably familiar with that term if you follow the weather closely. And so the atmospheric pressure at sea level is going to be right around 760 millimeters of mercury. We'll introduce pressure units a little bit more in the next slide, but if we use a mercury column, so basically what a barometer is it's a closed container that has mercury liquid in it, and the pressure on the outside, the gas pressure from the atmosphere, pushes down on the tray of mercury and forces some of it up into the glass tube. And so you basically just measure the height of that glass tube, and that gives you directly the pressure. Now we're not going to do the derivation for why that is, but all you have to do for these types of devices is measure the height of the column, and that will give you then the pressure that's being exerted on that substance. So in case of measuring atmospheric pressure, which is what we usually use a barometer to do, that's about 760 millimeters of mercury, or that's roughly 2 feet tall, 2 or 3 feet, not even 3 feet tall. So it's like a column about this tall off the table. Okay. The reason we use mercury and not water is because the height of the column is dependent on the density of the liquid. If we did it with water, you would need a column that's about 34 feet tall. Okay, so we don't want to use barometers that are 3-story houses, or as tall as 3-story houses. So we use mercury because it's a lot more dense, and we can use a column that's a much more reasonable size. All right, so these barometers are used to measure atmospheric pressure, and as I said, all you have to do is just read off the height of the column. That gives you the pressure directly in whatever units correspond to that substance, usually mercury. All right, if the other type of pressure measuring device is called a manometer, and this is for measuring the pressure of a sample of gas. So if we're doing experimentation on gas in a lab, we use manometers to measure those. So it's for closed containers of gases, not for like the atmosphere that surrounds us. And there are two types of manometers. So one is called a closed-end manometer. So what we have in a closed-end manometer, as the name implies, is that it's a sealed glass tube. It's a little U-shaped tube that has mercury in it also as the liquid. And so you're going to put gas in here, the gas is going to exert a pressure on the column of mercury, and it's going to push it down to some extent, and you're going to have a height difference now between one side and the other. Okay? So you measure this height difference. On the other side of this, at the top of the column of mercury, because it's closed off, this is just under vacuum. There's no pressure on that side. So in this case, you're going to measure pressure relative to a vacuum, meaning pressure relative to 0. And the change in height that we get, this difference between the two sides, as I've marked it here, that delta H is going to be just equal to the pressure of the gas in millimeters of mercury if you're using a mercury column. So for a closed-end manometer, we can again measure pressure directly. In open-end manometer, though, we have one end is open to the atmosphere. So what you have then is your sample of gas is going to be pushing on the mercury column. The atmosphere is going to be pushing back in the other direction. And it's sort of like, well, not really a tug-of-war because they're not pulling, but whatever you would call the pushing equivalent of tug-of-war, where the two are pushing on each other with different forces or different pressures. And so again, you're going to get a difference in height between the two, but you have two possibilities here. Either the height is higher on the side of the gas or higher on the side of atmosphere. All right, so this is what we call an open-end manometer, and here you're measuring pressure relative to the atmospheric pressure. So to get the absolute gas pressure, you also need to know atmospheric pressure using a barometer, so you have to use both in this case. And so the pressure of the gas is going to be equal to atmospheric pressure, whatever that is, plus or minus delta H, depending on which side is higher. Okay? So if the side of the barometer is higher on the gas side, that means the gas is pushing more weakly than atmospheric pressure. This is pushing down harder, so it forces the column down more on that side. And so in this case, it would be atmospheric pressure minus delta H for the pressure of the gas. In this case over here on the right side, it would be atmospheric pressure plus delta H. You have a height difference between the two. The gas is pushing harder, so the mercury column is lower on that side than an atmospheric side, and your delta H now represents the difference added to the atmospheric pressure. So a couple of differences there. You'll see homework problems on that as well, so I don't want to dwell on it too long, just to tell you a little bit about how we measure pressure. Now, equally important is the units for pressure and how to convert them. So the SI unit for pressure, if we're using standard units, is what's called the Pascal, named after the scientist Pascal, not surprisingly. And so it's abbreviated PA. So 1 Pascal is equal to, as we said, pressure is force over area. So the SI unit for pressure is Newton. So 1 Pascal is 1 Newton per meter squared, which is the SI unit for area. And so that's what a Pascal is defined as, where N is a Newton. This is not a unit that we use very much, so we're not going to do much with it, but it's equal to kilogram meters per second squared. So this all makes sense if you take in physics. This is the very physics definition of pressure. The more common units, though, for pressure are going to be the atmosphere. This is the most common that we'll use in this class. And we already introduced this again in the last chapter a little bit when we talked about expansion work. So the atmosphere, ATM, is the common unit for pressure, and is defined as the average atmospheric pressure at sea level. So atmospheric or barometric pressure, as we call it, because it's measured with a barometer. So the average atmospheric pressure at sea level is given as 1 atmosphere. And very often we measure pressures relative to that, because again, especially on the types of pressures that we work with in a laboratory setting, that's a pretty good starting point for us. So 1 atmosphere is related to the Pascal, but it's the Pascal is a pretty small unit, as it turns out. So it's going to be 101.3 kilopascals, or 1.013 times 10 to the 5th Pascal. So this is another reason why Pascal is not the most useful unit, because it's a very small pressure unit. So even 1 atmosphere of pressure is 100,000 kPa. You have to be dealing with huge numbers all the time. So we don't usually use pascals. We use atmospheres as a more convenient one. There's another pressure of bar that's basically 100,000 pascals, which is called the bar, another unit of pressure. So it's 1.013 bar. I don't think in this class we use bars much, if at all. So a bar and atmosphere are almost the same as each other, but bar is based on SI units, so it's a little bit more standardized in that respect, but we don't use it very much either. So the most common is going to be atmosphere. The other one that's common is torr, named after scientist Torricelli, who you might guess is Italian. And 1 torr is equals 1 millimeter of mercury. So as I said in the last slide, when you measure pressure with a barometer or a manometer, you're using mercury as the column, then you're measuring the height of that column to tell you the pressure. And so 1 millimeter of mercury is also defined as a torr. So those two are equivalent. These are used interchangeably, so we don't have to necessarily convert them, obviously, because they're the same thing. And there's no like context either when one is used and one's not. It's just whatever you feel like. And the important relationship, though, that you definitely want to know is that 760 torr is equal to 1 atmosphere. So we will use both of these quite often. So you definitely need to know this conversion between torr and atmosphere. We'll use that one all the time. Okay. So that's the units for pressure that we'll see most commonly. So just an example of how to convert them. This is just unit conversion, so there shouldn't be anything difficult here. If you get a compressed gas cylinder like the ones that you would use to blow up helium balloons or the ones that we use in the labs for all kinds of things that we do, those are usually supplied at a pressure of 2,000 psi. So psi, which you may have heard of also, is another unit for pressure, which is pounds per square inch. It's based on the British units, so we don't use it in science a lot, but it's used a lot especially in commercial applications for gas pressure analysis or gas pressure supplies. And so if we have a 2,000 psi pressure, what's the pressure in millimeters of mercury, where 1 atmosphere is equal to 14.7 psi, and 1 atmosphere is also 760 torr. That's one that you should know, as we introduced last time. So unit conversions for pressure are just like any other unit conversions. We're looking for pressure in millimeters of mercury, or in torr, as which is equivalent, as we talked about. We're starting with 2,000 psi. So we don't have a conversion factor to go from psi to millimeters directly, but we have one to go to atmospheres. So we can say that 1 atmosphere is 14.7 psi. This one you don't have to know off the top of your head, but we gave it to you here, so that we're going to use that one to go to atmospheres. We're going to use 760 torr per 1 atmosphere, and then as we said in technicality, 1 millimeter of mercury is the same as 1 torr, so this trivial last step here just converts into millimeters of mercury. Sorry, we won't cross that one out, that one we're keeping. Torr cancels out. And so what we end up with is 1.03 times 10 to the 5th millimeters of mercury or 100 meters of mercury. I didn't specify it in that unit. But what this also tells us here is that the reason we have all these different units of pressure is that it really depends on what context you're in, which one is most important. If we're talking about pressures that are atmospheric or close to atmospheric pressure, torr is fine. We go up to 760, and that's not too big of a number. But if we're talking about relatively high pressures, like in a compressed gas cylinder, torr is or millimeters of mercury is a pretty useless unit, because you need a mercury column that's 100 meters tall, 300 feet tall to measure that. So again, the different units that you use often depend on just the context you're working in. They're really interchangeable depending on what you're doing. All right, so that's just a little bit about units of pressure, but the more of these problems we'll do, you'll see these all the time. So what we're going to finish up today introducing are what are called the ideal gas laws, and then we're going to combine them next time into one overarching gas law. So there's 3 that we want you to know and be familiar with, and all of these are basically relationships that involve the volume of a gas and how it changes with respect to other parameters for that gas. So thinking back to the early days of chemistry when a lot of these laws were developed, volume is a pretty easy thing to measure, right? You just have to measure how big the container is that the gas is in, and use like movable pistons that can move up and down, figure out what the volume is as the gas stabilizes. And so volume is a pretty easy thing to measure, and then a lot of these early scientists, they measure the volume of the gas and how does it change when we change other things about that gas. We're going to talk about pressure, temperature, and number of moles today, okay? So let's go to a video that illustrates Boyle's law. So in Boyle's law, we're working at a constant temperature and the container is closed, that no gas escapes on us. And we're going to do a demonstration now that relates the volume and the pressure, which is what Boyle's law tells us, okay? All right, so what we have here is some demonstrations of Boyle's law. So we have a balloon in this container, and he's pulling vacuum in the container. He's basically reducing the pressure inside the container by removing the gas that surrounds it. And what you can see is that as he lowers the pressure, the balloon is getting bigger and bigger and bigger. So lower pressure, larger volume, telling us that pressure and volume are inversely related to each other. As you decrease the pressure, you increase the volume. And then when he's going to release the vacuum and let the system repressurize, the volume goes back down. So as the pressure goes back up, the volume goes back down. This being Easter season, he's going to do the same thing on a marshmallow peep, which has a lot of gas trapped in it. And so he's going to seal this into this container. He's going to pull vacuum on the container to lower the pressure, and the peep gets bigger and bigger. This time it's not completely reversible because the mechanical properties of the marshmallow are not exactly what they need to be, and so you can see it collapses. So he's raising the pressure now, and you see that it collapses back down. This is shaving cream, which also has a lot of gas trapped inside of it. Lowers the pressure of the container. We see that the gas that's trapped inside the shaving cream expands its volume to respond to that, and the whole thing sort of blows up like that. Okay?
The pressure outside is lower than the pressure inside. The shaving cream will expand.
All right, so that's not a magic trick. That's just shaving cream. And then I don't know if he releases this one or what happens or not. If we're going to show that, he did not show what happens when he releases that one. All right, so we see from those demonstrations of Boyle's law. Get out of here. What we saw was that volume and pressure were inversely related to each other. So volume is inversely proportional to the pressure. So we write that out in words as V is inversely proportional to P, meaning as one gets smaller, the other gets bigger. All right. Now, because we have this proportionality, what that means is that we can write it as an equality by saying that volume is proportional to a constant over the pressure. We put a constant on one side of the equation. Now this constant is ill-defined, as we'll see, because it depends on how much gas we have, it depends on the temperature, all that stuff, so we're not going to actually use this equation. But if we rearrange this, we see that the product of pressure and volume is equal to a constant K. Oh, jeez, come on. All right, so the product of pressure and volume is equal to a constant, so that means whatever that product is, whether we increase one, decrease the other, or vice versa, the multiplication of those two always gives us the same constant number for a gas at a constant temperature, which means we can take then the initial and final states and set them equal to each other because the product of pressure and volume will never change. So we write P1V1 equals P2V2. And so this is a mathematical expression of Boyle's law, which says that the product of pressure and volume will be equal to the product of pressure and volume after we change them, as long as we're keeping temperature constant and the number of moles of gas constant. Okay? So that's Boyle's law. Now, as we'll show you next time, we don't need to memorize all of these equations individually, but that's what the relationship between Boyle's law involves volume and pressure, and we should definitely know that. All right, so here's an example of a Boyle's law problem. Let's say we have a balloon. We inflate it to half a liter at sea level. We release it to the atmosphere, and it goes to an altitude of 6.5 kilometers. The air pressure there is 0.4 atmospheres. So at sea level, we're starting with an initial pressure of 1 atmosphere. We didn't tell you that directly, but that's the initial pressure at sea level is 1 atmosphere. This is our initial volume, V1. And then our final pressure, P2, is 0.4 atmospheres. What will the final volume of the balloon be? So this is a Boyle's law problem because we're assuming that the temperature is the same, which is probably not a good assumption because I don't think the temperature in the atmosphere is the same as it is on the ground, but let's suppose that it is, and ignore the fact that the balloon has some elasticity. So if we're just dealing with pressure and volume, we know that P1V1 equals P2V2. This looks a lot like the M1V1 equals M2V2 equation that we saw before for molarity, but it means something totally different, obviously. So we're solving here for V2, the final volume when it raises to this lower pressure atmosphere. So V2 is going to be equal to P1V1 over P2, and we just plug these in. And for these equations here, units don't matter as long as they're consistent. So if we put 1 atmosphere in the numerator as P1, and V1 is 0.5 liters, and then in the denominator we put P2, as long as it's the same unit, it's atmospheres in the numerator, so it also needs to be atmospheres in the denominator. Those units can be whatever they want. All right, because atmospheres cancel out, and then we have an answer in liters, which comes out to 1.25. So our balloon will, in this case, more than double in size, go to a volume of 1.25 liters in the upper atmosphere. As long as the material is strong enough, it won't necessarily explode on us, but it will expand its volume considerably. All right, so that's an example of Boyle's law. Relatively simple. We will sometimes use it by itself, but as I said, we're getting to a more useful gas law that we're working towards. All right, the next law looks at what happens when we change the temperature of a gas. Okay, so we have, in this case, we're using gas at a constant pressure, so we're not allowing the pressure to change in the gas. We have a closed container, so no gas escapes, but we're going to see what happens when we change the temperature of a sample of gas. And so we're looking at the relationship between volume and temperature for Charles's law. All right, so we have another demonstration of this one here. So in this demonstration, we're going to take a balloon, which is filled with gas, and we're going to cool it down using liquid nitrogen. All right, now this person has no regard for their personal safety because they're not wearing any sort of gloves, which they probably should if they're working with liquid nitrogen. So they're taking the balloon and they're cooling it in liquid nitrogen. As you can see, the balloon is shrinking. So as the temperature goes down, the volume of the balloon goes down. Okay? So there's a direct relationship in this case between volume and temperature. Now, and he's going to take it out, let it warm back up. And so as the temperature of the balloon increases, using the scientific technique of blowing on it to increase the temperature more rapidly, you see the balloon blows back up and its volume goes back to where it started. So as the temperature of the balloon increased, the volume also increased. So we would say that those two terms, volume and temperature, are going to be... Oh, come on. This is dangerous. I don't want to accidentally watch another video. All right. Shoot, still going. Close. All right. All right, so we saw in this case that volume and temperature are directly proportional, which means we would write the relationship as this. Volume and temperature are directly related. That's how we write it mathematically. V is directly proportional to T. Or we could write it as volume is equal to some constant times T. Now, to make sure I'm clear, it's not the same constant as last time. It'd be K prime. Where again, this is true if we keep the pressure and the number of moles of gas the same. So if we rearrange this one into sort of an initial and final state, V1 over T1 is equal to V2 over T2. So basically, we move temperature over to the same side as volume. And so the ratio of V1 over T1 for the initial states will equal the ratio of V2 over T2 for the final state. Now, as I said, in Boyle's law, the first one we did, the units aren't so important as long as we keep it consistent. Here, the units are critical. So if we're ever using absolute temperature, we saw in the last chapter that for delta T, it doesn't matter. But if we're using an absolute temperature, it needs to be in Kelvin. Okay? So for anything you do with gas laws in this chapter, make sure your temperature is in Kelvin. That's sort of the short of it. So we have to remind ourselves that to convert between Celsius and Kelvin, the temperature in Kelvin is the temperature in degrees Celsius plus 273.15 if we're being really precise. So we have to make sure that we use the correct units of temperature. This relationship does not work if our temperature is in degrees Celsius or any other temperature unit. It has to be Kelvin for this to work. Okay? And that's true for any of these equations that use the absolute temperature by itself, not as a delta T, but as an absolute temperature. All right, so that's the second gas law, which is called Charles's law. So a quick example problem for that one. We have a sample of gas that has a volume of 79.5 milliliters at 45 Celsius. What volume would it occupy at 0 if the pressure were held constant? So again, this one is telling us about the relationship between volume and temperature. So we have our initial volume and our initial temperature. We have our final temperature, T2. So we're looking for what is the final volume, V2. So Charles's law, as we said, is V1 over T1 equals V2 over T2. We're looking for V2, which is going to be the product of, if we cross multiply, V1 times T2 over T1. The units for volume don't matter. They're whatever we want them to be. So we're going to put in V1 as 79.5 milliliters. But the units for temperature, as we said, are critically important. And here I think it's fairly obvious because T2 is 0 degrees Celsius. If we put 0 degrees Celsius in for T2, that would mean our final volume is 0, which is completely nonsensical. You don't go to 0 volume when you cool something to 0 Celsius. So we have to make sure we get our temperatures in Kelvin. So the initial temperature in Kelvin is going to be 45 degrees Celsius plus 273. The 0.15 is not that important. As long as we do it as 273, that's going to be fine for anything that we do. T2 is going to be 0 degrees Celsius plus 273 to make it into Kelvin. So that's going to be 318 Kelvin, 273 Kelvin. Okay? So T2 is the one that's smaller, 0 degrees Celsius. So it's going to be 273 Kelvin there. T1 is 318 Kelvin, so they have to be in Kelvin again for this to work. So Kelvin divides out, our answer will be in milliliters, and we get 68.2 milliliters. So a small decrease in volume, but not dramatically different in this case, because again, the absolute temperatures even though 45 degrees to 0 degrees sounds like a large difference, and in our scale it is. 45 degrees would, that would burn you if you went into a hot tub that was 45 degrees, whereas 0 degrees you would freeze to death pretty quickly in that temperature. So on our scale that seems like a huge difference, but the absolute temperature is small, so the volume change is small. All right, last one to go through is Avogadro's law, which this is what Avogadro actually did. He didn't do the number, he did the law. And this one is related to number of moles. I don't have a video for this, but I think this one is fairly obvious to us. So it's constant temperature and pressure. This time we're going to use N as the abbreviation for number of moles. Okay, so that abbreviation is going to start coming up a lot, using N for number of moles. And what do you think happens, whether you can read this or not? I mean, you can see it here, but if you take a balloon and you add more moles of gas to it, it's going to get bigger or smaller. Okay, I think we're all clear on that one. If you blow up a balloon, the more air you put into the balloon, the bigger it gets, right? So volume, in this case, is directly proportional to the number of moles, okay? That means volume could be written in an inequality as a constant, which I'll call K double prime, just make sure we know it's not the same constant. But again, this constant is not very well defined because it depends on the temperature, it depends on the exact pressure. So what we do typically is rewrite this as a ratio and set initial and final conditions equal to each other. So the most useful form of Avogadro's law is that V1 over N1, again moving this to the other side, and it's going to be equal to V2 over N2. All right, so that's a statement of Avogadro's law. In this case, remember that N1 and N2 are the total number of moles of gas present before and after. It doesn't matter how much we're adding or subtracting, it's the total number, not the difference. So this last example here, if we have, at a certain temperature and pressure, we have 28 grams of N2, which occupies 20.8 liters, how much volume does 40 grams of O2 occupy at the same temperature and pressure? So we're talking about different numbers of moles of gas, different amounts of gas, and we're talking about volume and number of moles, so we're going to use Avogadro's law here. Now, one thing that we notice about Avogadro's law is that it doesn't depend on what the gas is, right? It's just number of moles of gas. So something that will become more clear as we go later on through this chapter is that for all of these gas laws, we don't care what gas it is. For any gas, they all follow. And so even though we're comparing two different gases here, nitrogen and oxygen, this relationship between volume and number of moles will hold even though the two different gases even though it's two different gases, because this equation doesn't have anything related to what the gas is. All right, so we're looking here for the final volume V2, which is going to be V1 times N2 over N1. So our initial volume was 20.8 liters. That's that number there. But we need the initial number of volume, the number of moles. So N1 is the amount of nitrogen that we're looking at. So we have 28 grams of nitrogen, and we know by now how to convert grams into moles by using molar mass. So we divide by the molar mass. So 28 grams of nitrogen is exactly 1 mole. So that's our initial number of moles. N1 is 1 mole of gas for nitrogen. We want to see how much volume a different amount of oxygen occupies. So for O2, which is our N2 in this case, number of moles of oxygen, we have 40 grams. The molar mass of O2 is 32. So we have 1.25 moles of O2. So if we have 1.25 moles of O2, the volume will increase by a factor of 1.25. Moles divide out, and we get 26 liters in this case. Okay. So whether we're comparing two of the same gas or two different gases, if we change the number of moles, we also change the volume. So next time we're going to learn how to combine all these gas laws into a more useful equation. That's going to be the one that we're going to typically use going forward. All right.